And so last time you guys talked about one way to distribute content on the internet, right? You learned about servers and about content distribution networks and how things like YouTube and Facebook and so on distribute their content. And so today we're going to continue that sort of line of thought and look at other distribution models. So we're going to look at peer-to-peer and then data centers. So, or the cloud is the marketing term now is. So these both achieve the same goals, distributing files, but they're going to do them in very different ways, and we'll go into exactly what the differences are. So before talking about these, I just want to briefly review the sort of the standard distribution model, which is where you have a server. So I'm not a great artist, so this represents a server. Okay, so we have a server somewhere, and it has a fast network connection going out of it, connecting it to the rest of the internet, right? So now we can share files from this server. This file can distribute content to anyone on the internet who can reach it, but this doesn't necessarily work that well when we get into large scale, because this server is sort of the limitation. And also this pipe here, however much bandwidth we have, this could also become a bottleneck. So peer-to-peer is one technology that gets around some of these scaling limitations of just this single server model, where with peer-to-peer, each of the people downloading a file can use their uplink bandwidth to also contribute in distributing the file. All right? So let's just sort of frame this discussion of peer-to-peer. And first of all, what's the goal of peer-to-peer? It's really, I mean, the goal, file sharing and so on is one thing we can do with peer-to-peer, but the goal really is efficient use of resources. And now I'm being generic here and just saying resources, because this may be bandwidth or maybe CPU or memory or some scarce resource in our system, okay? Most of the time it's bandwidth, though, is the resource we want to share. And so we'd like to design a way to distribute files that's as efficient as possible, okay? That's our goal. And peer-to-peer is an application layer technology, which you guys have been covering. So it's also at the application layer, like things like DNS and HTTP. And because it's at the application layer, it means it's software running on the end hosts. And so let me just draw what we have here is we sort of have these end hosts connected to the internet. So now we have multiple end hosts here. And these are all running some peer-to-peer application, and they form what's called an overlay network. So this overlay network is just a network that links together peers in this peer-to-peer system. So let's suppose that they're all linked to each other. And these green links here represent these logical links. That is the application layer connection between these different peers. And so when there's this logical application layer link between two peers, we say that they are neighbors, okay? So each end host in our peer-to-peer system is called a peer, and then the connections between them, if two peers are neighbors, or if they're connected, then they are neighbors, okay? So that's just some basic terminology. And then this green part, this green logical network, is called an overlay network. Okay, so now these logical links might go over multiple physical links. For instance, this peer may be connected to the internet through Wi-Fi, which then goes across some access network to a transit network and so on. But we can abstract away all those multiple links into just this one overlay edge, okay? Now, so if you recall in our discussion of the internet in general, we said that one definition of the internet is basically everywhere that you as an end host can reach, right? You can only see a portion of the internet at a time. Well, peer-to-peer systems are exactly the same way in that there may be many, many nodes or many, many peers inside the peer-to-peer system that you cannot directly, you're not directly neighboring with. And that's okay because each of these peers has a different view of the peer-to-peer network, of this overlay network, okay? And so they know their own neighbors and that's it. But if we look at everybody's neighbors and their neighbors and so on, then we can expand it out into this big overlay network, right? Okay, so one important thing I want to say about peer-to-peer networks here is that, you know, in standard networking, we route to an address, right? The way you guys have learned so far is that each host has something like an IP address or MAC layer address, which you haven't totally talked about this stuff yet, but you know a little bit, right, that everybody has an IP address. So if you know this peer's IP address, you know the network knows how to reach him, right? So peer-to-peer networks, these overlay networks are a little bit different in that we route on content, not on addresses. So in other words, this peer isn't saying, connect me to this server, this other peer. It's saying, I want this content, find that for me. All right, so that's an important distinction that these are content routable networks. And we'll talk a little bit more about that throughout the lecture. So can anyone tell me what are some other reasons you might use peer-to-peer? So we talked about, you know, sort of the goal is efficient use of resources, but why else might you want to use peer-to-peer? Okay, yeah, I mean, yeah, so there's like multiple copies of the content, right? And it's spread out. It's probably distributed, you know, maybe throughout the world. So there's better replication and so on. If somebody loses their copy of something, then somebody else in the world probably has it. So what do most people use peer-to-peer for these days? Yeah, so for illicit purposes, essentially, right? So one major reason for it, and the reason they're useful for, you know, downloading illegal content and these things is because they provide anonymity, right? I don't know if I can spell this word right. Anonymity. All right. However it goes. Anyway, so yeah, let me fix this. Anonymity. Okay. Anyways, so they provide some amount of anonymity. Anyways, they make you almost anonymous. Now, we'll see that you're not entirely anonymous when using a peer-to-peer system, but it is harder to figure out what you're sharing and so on. So we'll talk about the Bittorrent protocol next and look into that. And then, so finally, we already touched on this, but the final major reason to use peer-to-peer is this efficiency. And so just to sort of visualize the efficiency is if we show this chart with here we have the number of peers, so these are the number of hosts trying to download a file, and then here we have the time for everyone to download the file. Okay, download. So if we were to use this standard model where we have a single server that's distributing to all these different peers, let's say between, I mean, this chart's not going to be precise, so it doesn't exactly matter, but just to give you some scale, say we have up to 100 peers. So if we took a standard server, the standard server client setup, it would probably look something like this. Meaning that, you know, as there's more peers to download it, then the amount of time it takes to download the file for everyone is directly proportional to the number of peers, right? So they each add the same amount of time, so it's just a straight line. But in a peer-to-peer system, things happen much quicker, and this is because each peer is utilizing their downlink bandwidth as well as their uplink bandwidth. And so things look a little more like this, where they sort of taper off as there's more peers. And so we have this sort of logarithmic growth instead of a straight line. All right, so let's move on to talk about Bittorrent. So Bittorrent is a very popular peer-to-peer file sharing protocol. Its first implementation was in 2001, although it didn't start to become popular for a few years after that. Okay, so the main concepts are, first of all, we have this thing called a torrent. So the key to the overlay network yes, so that's exactly correct, that it's the key to the overlay network, and we'll talk about what exactly that means. And then also, as you mentioned, it contains sort of the description of the files. Right, so these are the files that are in the torrent and that will be downloaded by your Bittorrent client, okay? All right, so this is what a torrent is, and then so there's these things called trackers. All right, so a tracker is sort of a centralized node that keeps track of all the peers in this overlay network that we've talked about, okay? So they keep track of the peers. Okay, so they keep track of the peers, and they keep some information on each peer, like if one peer wants to contact another one, then it needs the IP addresses. And then it also keeps details about how much content each peer has shared with each other. So let's just say sharing statistics. Okay, and so these sharing statistics are important because we'll talk about this problem of free riders and leechers and so on. So the tracker wants to keep track of some sort of statistics to sort of give more bandwidth to the people who are sharing more and so on, okay? All right, so these are sort of the main parts of Bittorrent is we have this tracker, which is more or less a centralized node that's keeping track of all the peers in the overlay network. And then we have these torrent files, which each torrent has a unique overlay network, okay? And then each torrent has how to get into that overlay network, and then it also has a description of the files that you'll be downloading as part of this torrent, okay? All right, so now we sort of have the basics. So a tracker is this sort of thing that's like a centralized node that keeps track of different torrents. Each torrent is an overlay network where the peers are sharing these files in here, okay? So it's just some common trackers. Does anybody know like a common tracker? So the Pirate Bay, for instance, is a very common tracker. And these trackers are, you can have multiple trackers per torrent. So meaning that one torrent could be listed at like 5 different trackers. So if one of these trackers gets shut down, then you still have the other 4 that can be used to share the files. Okay, so let's get into now actually the operation of BitTorrent. Okay, so let's go into the example of how it works. So suppose that this server here has a torrent that it wants to share, and So the first thing that the BitTorrent protocol does is it divides these files up into what are called chunks. And each chunk is just a small part of the file. Typically they're like 256 kilobytes or so. If you're downloading, like huge movies, there'll be a couple of megabytes. But it breaks it up into chunks so that it can get a chunk from anywhere and it doesn't matter where you got it from. So let's look into this. So we have this torrent here at this machine, and let's say it's broken up into 4 different chunks. Okay, there's a green chunk, a blue chunk, an orange chunk, and might as well get another color. And then a pink chunk, okay? So this node has the file and it's initially uploading it, and so it's called a seeder. Okay, so seeders are peers that have the entire file and are just uploading to other peers, okay? Whereas peers are typically uploading and downloading. And then there's other nodes, they're called leechers, and they are just downloading. They're not contributing anything back to the torrent, okay? Or anything to other peers. Okay, so the way this works then is that, so suppose this node just joined the overlay network, so it just registered with the tracker and said, I would like to download this torrent. So the tracker says, okay, here's the IP addresses of a bunch of peers in this torrent, all right? So then this node gets the IP address of other peers, and it initiates connections with them and asks them for a chunk of the file. So in the torrent description, this peer knows that this file has 4 different chunks, and so it needs to ask other peers for those chunks. So it registered with the tracker, now has connected to 3 other peers, and so it asks them for a chunk. Well, this peer and this peer don't have anything to provide it with, but this seeder has some chunks, so let's say it sends it the pink chunk, okay? And at the same time, this node was also downloading the file from this seeder, and let's say that it got the green chunk in the same time period, okay? Okay, so now we're at some point in the future where these 2 nodes have completed those chunks, and so it looks something like this. And we have this server now has connected to this host has now connected to the torrent and has become a peer, and so it wants some content. So it asks these 2 for content, and these 2 also ask. So this peer they exchange information about what chunks they have every 10 seconds. Okay, so this peer sees that this peer has the green chunk, and this peer has everything. So what it does is it asks for the rarest chunk first. So it knows that the rarest chunks in the system right now are the orange and blue chunks. All right. So it asks the seeder for one of those 2. Let's say it asks for the orange chunk. And so let's just draw an arrow showing where it got it from. And then it asks this peer for the green chunk. So this one sends it the green chunk. And then let's say that during that time step, this peer had also asked the seeder for the orange chunk, right? Because they didn't coordinate what chunk they were going to ask for, so it's possible that they got the same chunk. Okay, and now during this time step, this node asked this node for, he had the green chunk before, right? So he gets the green chunk from here. And then it had asked this node for this pink chunk. So it gets the pink chunk. Okay, so that's the end of the second time step. So what happens now is, all right, so we're at the end of the second time step. So let's say now the third time step starts. Okay, so this leecher is going to ask this node for one of these two nodes for the orange chunk, right? Because it has the other ones. And then these guys will ask the seeder for something for the blue chunk because it's the rarest chunk. So this guy, let's say, gets the blue chunk from the server. And then this guy, let's say he asked the leecher for the pink chunk and asked the server for the blue chunk, or sorry, the seeder for the blue chunk. So it gets the blue chunk from the server, but this guy is a leecher and doesn't want to share. He doesn't want to give him the pink file. So during this time step, he's asked for the orange file from here, and that's it. Let's say, but so this peer would like this guy to send in the pink file, but let's say he refuses. Okay, so what's going to happen is this node then won't share any data with this leecher because he knows that he is a leecher. He's not sharing at the same rate. So he doesn't get this pink file. He basically will drop. After some amount of time, he'll drop this connection with this other node and say, "Okay, you're a deadbeat. I'm dropping you, right?" And this node, so say that this node also didn't request. So this node, let's say, eventually requested something from the leecher, and the leecher didn't share with him. He gets dropped. Okay, so probably in the future here, then this guy would have got pink chunk from the seeder. So these guys have everything, but the leecher doesn't. Now, unfortunately, it's not impossible for the leecher. The leecher can still finish this file download. I mean, I don't know if that's unfortunate. It's actually good for me in real life. But anyways, so this leecher can go ask the tracker for more peer IPs. And there'll be some more peers, like let's say out here, there's another peer, and so on. And so it asks the tracker for more peer IPs, and it will just connect to these additional peers and get one chunk from each of them. And then maybe after that one chunk, they'll drop the connection, but it can still, there's enough, as long as there's enough peers in the system, it can still manage to download the entire file. Okay? So this problem is known as free writing. Because some nodes are able to get away without sharing. Yeah, I mean, so this brings up one final point before we take a break, is how many times does the seeder need to actually seed the file, like send the file to somebody else? Like, so let's say we would like all of the peers to obtain a complete copy of the torrent, right? So, and there's only one seeder. So how many times does this seeder need to upload the data? So he needs to upload every chunk at least once, right? And that's it. As long as somebody else has a copy of the chunk, of every single chunk, then the entire file is out there and all the other peers can get it, okay? And so that's why really peer-to-peer is more efficient, is because these peers are utilizing their uplink bandwidth, so this initial seeder doesn't have to send it to everyone. It just has to send it to one person, and then he can send it to the next, and so on. Okay? So the way it works is you actually have a top 4 peers. Typically it's 4, but you can change it. But so each peer will keep track of their top 4 other peers, which are the ones they've gotten the most data from in the last 30 seconds. And then they initiate one new random connection every 30 seconds and try and find a better peer. And so then they keep dropping off their worst peer every time. All right, so there's a couple things we haven't talked about. So one is, how do you locate content in a peer-to-peer network? Okay, so does anybody know? Do you have an answer to that? So if you're using peer-to-peer, how do you find, like, whatever, avatar, something to download? So there's, all right, so let's, one is like a tracker search engine, right? Tracker, I guess it's actually not, it doesn't search for trackers. It searches for torrents. So let's say a torrent search engine. Yeah, examples are like the Pirate Bay, ISO Hunt, so on. Okay, so that works for Bittorrent because Bittorrent has this idea of these trackers and these torrent files, but it doesn't necessarily work for all peer-to-peer systems. So there's other models. So one is a centralized directory server. Okay. And now Bittorrent is sort of a mix between the centralized and the fully distributed case, all right? So we're going to look at each of those, and then you'll see how Bittorrent fits in. So you can have a centralized directory service. This is, for example, what Napster did. Okay. And this centralized directory sits out here somewhere and is connected to every single peer. I'm not going to draw all the links because I want to use that picture, but the directory service then asks the peers for what are every single file you have. All right, what files do you want to share? What's your IP address, and so on. So if a new peer comes online, a new peer is here, it comes online, it first contacts this directory server. The directory server says, oh, you have, okay, I'll index all the content you have, and so on. And then if you're searching for something or you want to download something, all your searches go to the directory server. The directory server looks through all its content and then replies with the IP addresses of the peers that have those files. And then this server can then connect to the peers that have the files it wants to download and get them. Yeah. Yeah, okay, so say I'm searching for, I don't know, something, I used Avatar before, let's say Avatar. So you're searching for Avatar. This search doesn't go to your peers, it goes to the directory server, okay? The directory server knows the file list of every single peer in the system, all right? So it knows what files each of these other peers has, and so it says, oh, okay, I know who has Avatar, and it says the IP addresses of the peers that have Avatar. All right, then this server can connect to them directly and get Avatar from them. So the way you would actually arrange the files on the server, so it doesn't have the actual files themselves, it just has the metadata, the information about the files. And so it's not going to store them in like directories and so on. It's going to store it in like a hash table or something, some other data structure. Okay. So the question is like, so suppose we're starting this out. There's only one peer, right? And then he's going to say, oh, there's no other files in the system. Well, I mean, so you guys are probably too young to have used Napster. It came out when I was in middle school, and it worked. I mean, like Napster used exactly this model. But it just got to the point where enough people left it on for long enough, and it was originally like craftily written to run in the background all the time and so on, right? So it worked that enough people got started and then you could find content. Yeah, so I mean, it is sort of this chicken and egg problem, but it seems to be okay in practice. But there are other, so let's go over sort of what are the advantages and disadvantages of this type of having a centralized directory. So what are the advantages? Yeah, so you don't need some sort of search engine, or well, I mean, in a sense, this is sort of a search engine, but But you don't, yeah, no like third-party search engine. What about ease of programming, right? This isn't that hard to implement because in Bittorrent we use these trackers and so on. It was a little bit harder to find peers, whereas if you have this centralized directory server, you can just ask it, what are the peers I should connect to, and it does it. So the client software is much easier. This directory software might be kind of hard to write because you have to keep track of so much data, but I think overall it's easier to implement. Okay, but what are the disadvantages? So there's like one point of failure, right? And if you are a Napster and people are sharing illegal content with your service, and music corporations want to sue you, there's an easy place they can go after, right? They can just take this directory server down, and then all of Napster goes away. Okay. So that's the big disadvantage with this, is that there's one point of failure, and then this is also very hard to scale. This server needs to keep track of the files that everybody has, and so that can be really hard to scale so that it can answer these search queries from hundreds of thousands of users. Okay, so let's look at one more method of search, and that's a completely decentralized approach. So, okay, the way decentralized search works is that we don't have any sort of centralized nodes. So we don't have the centralized server. We don't have like a torrent search engine or anything like this. So what do? So you need some way to like join this network, right? So I'm saying like, okay, assume we have this network, right? So there does have to be some centralized mechanism or some known peers to get you into the network. Yeah, you need that. Okay, but the search process is very easy. Just every node just floods the query, and then you can put a limit on that. Like you can say only flood for 7 steps or something. All right, so there's obviously illicit file sharing is the biggest use case for peer-to-peer, but there are other uses of it. So one company that does use it in a legitimate way is Skype, and they use peer-to-peer. So you guys last week or the week before talked about NAT, this network address translation, and if you have 2 machines behind a NAT box in the network, then you have to like punch a hole through your NAT and make an opening. But if both users are behind NATs, you can't do that. So Skype uses peer-to-peer to have peers that are not behind of NATs, and then these other peers go through this peer in order to get around their NATs. So if you use Skype running on a machine with a public IP address, like any machine on campus, for instance, if you leave Skype running, odds are you're going to be relaying a lot of calls for other people because that's what it does. It forms this peer-to-peer overlay network and uses your resources to help other people make phone calls to each other. Yeah, which, so Skype is free, I guess, so you can't complain too much, but, you pay for that freedom they do use some of your resources. And then, so other legitimate uses of peer-to-peer is Skype, and then it's often used commonly inside of data centers. So, for instance, Facebook uses BitTorrent internally, so they have a new version of Facebook, and they want to roll it out. Well, Facebook has now like 70,000 servers, okay? So they need to distribute this update to all 70,000 servers. Well, the most efficient way to do that is just use BitTorrent, and then they all share it, and then every single server has it, okay? All right, so let's move on to now talk about the cloud. Okay. So this term is super hot right now, but can anyone tell me what it means? So a data center. So centralized content. Okay. Yeah. Remote computing. Okay. About what is Gmail, for instance, or Google Docs? So they're applications, right? But where do they run? So they run in Google's servers, their data centers somewhere, right? So we could also take the view that the cloud is these sort of online or on-demand applications. Yeah, so, well, okay, I don't know exactly what you mean by remote computing. So let's just say that. All right, anything else? Has anyone used things like Amazon EC2, renting, I'm gonna say compute power. So yeah, I mean, so the cloud is sort of all of these things at the same time. So in the first lecture, Keshav asked, well, what's the internet? And there's sort of two different views you can take. You can take a service view, the internet provides this service, or you can take this hardware, like physical layer view, that the internet is this collection of hardware devices. So we can take the same view with the cloud. And so the first view is this sort of the physical view. And this is, this is essentially this data center definition. So the cloud is a bunch of data centers. Okay. But then what is a data center? It's a warehouse just full of servers. Okay. And so the way these things typically look is we have a rack here, and this rack has a bunch of partitions. Each of these is called a slot, and then they're about the size of a pizza box, and then one server goes into one of these slots. And these servers, I mean, they really are, they're super thin. They're about a meter wide, or not quite a meter, like half a meter. And then these racks are typically 2 meters tall. And they hold, with these pizza box size servers, there's typically about 40 servers per rack, 40 or more, 40 to 80. And then you arrange these racks into rows, and each row, so this is a row, and each row has something on the order of 1,000 to 4,000 servers. And then these rows can either be a standalone row of these rows of racks, or what's common is to put these in a shipping container. So when you're driving like on the 401, you see a big, like a semi-truck driving by, and they're pulling this container. So you can actually take those off of the trucks and take the wheels off and everything, and they're shipping containers, and then you can pack them full of servers, and this is called a modular data center. And you can just pick these things up and move them around, and they contain about 1,000 or 2,000 servers. And so then we combine these rows and so on and form data centers. And a typical data center has more than 10,000 servers. So generally 10,000 to the biggest data center now today is Microsoft's data center in Chicago. And I'm not sure if it's fully built yet, but when it's fully built, we'll have over 200,000 servers. So these things are just huge. Like the scale of these is gigantic. And as you can imagine, that creates a lot of problems. So we were sort of, in the beginning of class, we were looking at peer-to-peer as a way to gain efficiency, because what happens when we pack 200,000 servers into a big warehouse is things get really hard, because each of these servers uses, a fair bit of power, and when we have that many in a small space, the number one concern is cooling. So, I don't know if you've ever had like a computer or something under your desk at your feet, but it's a good foot warmer, right? So if you have 200,000 of these in a building, then you need to cool it. Cooling is often very expensive. It's one of the major costs. Major cost of these data centers, and also, so modern data centers are using this free cooling by just opening the windows. So they're often locating data centers in cool regions to take advantage of the free cooling. Like for instance, there's lots of data centers now in Ireland, in Belgium, in like the Washington State area and so on, because these areas, the temperature never really gets above, say, like 25 degrees. And at that temperature, you can just use the outside air to cool your servers. Okay, so this is sort of a rough view of the physical view of of the cloud. It's these data centers, which are just giant warehouses full with many, many servers. But we also said we can take a service view of the cloud, and that is looking at the applications that the cloud provides. So what are some examples of cloud applications? Okay, so exactly, yeah, Gmail or Hotmail, iCloud. Yeah, iCloud's not exactly an application, but yeah, it's a service. So hold on, Gmail, iCloud, Hotmail. Okay, so WhisperNet. Okay, so yeah, Dropbox. That's a good example. YouTube, yeah, YouTube is a cloud application. So YouTube is essentially doing content distribution, right? But it's using data centers to do that content distribution. Okay, so there's a few others that, so this is essentially just content distribution, streaming video. Siri, I think, is a good example of a new cloud application. Because this is an application that wouldn't be possible. I mean, it is possible to do it on the end host, like you could do this on your server, but it's potentially better in the cloud because it can get smarter from the aggregate data of everyone using it. And the more data you have in some of these problems, then the better your results are. So that's why it makes sense to move some things like spam classification, for instance, like filtering spam. It's done, much better in the cloud where you have more data. Okay. Okay, so there's other ways we can think of the cloud too. Like someone mentioned that the cloud is, like renting compute power online, or this remote computing idea. And so this is sort of the data center view. So, networking people like to break things up into layers. So I'm sure you've seen the 7-layer model of the internet. You have physical and so on up to the application. Well, the data centers are the same way. Up at the very top, we have the applications. And these are things like Gmail and stuff. And down here, we have the servers, essentially servers and hard disks. Okay, but what's in between these things? There's some building blocks that make it easier to build applications on top of these servers. So keep in mind, if we have a data center with 200,000 servers, and we're just going to say, okay, let's write an application to go out and use all these 200,000 servers, that's pretty hard to do. You have to know the IP addresses of all the servers, and you have to manage these connections and so forth yourself. So it turns out there's some things that make it easier to write these cloud applications, and these are called platforms. Okay, so you don't really need to know what a platform is. I just want to say that these are things that make writing cloud applications easier. And they make it easier because they provide some functionality for you. So they'll provide, and this This, by the way, is called Platform as a Service. And there's things like Windows Azure that, so it basically allows you to buy compute time on Microsoft servers, but they have this platform called Windows Azure that if you write your application on top of their platform, you get things for free, like you get auto scaling. And this means that, so suppose you have one server that's hosting your website, and then /dot links to you. I don't know if you guys know this in terms of /dot effect, but /dot is this popular tech blog. And when they link to websites, the websites tend to crash because they're not meant for this. They're on like some cheap server somewhere. And so then suddenly they get 100,000 visitors and their server can't keep up. So the server either just crashes or starts to deny requests. But one thing you could do is if you were smart, you'd have this one web server, but then suddenly you get a lot of hits, you get more traffic, so then you split it off and create two web servers. And you use these things like this DNS tricks to load balance that you guys talked about last time. Well, you could keep doing that and grow your service to hundreds of thousands of servers if possible, right? And so if you build on top of one of these platforms, they do this automatically for you. So they'll notice, oh, this server is getting heavily utilized, and they'll create a new server for you and start running your code there as well. Okay. So yeah, I just want to say what these things sort of get for you. They get you this scaling, they get you reliability, and they just basically make your life easier. They keep your data. So one problem is, so say you have a server, it's running, and then your hard drive crashes on it. Well, you need to have a backup copy of that data somewhere, right? Well, if you build on top of one of these platforms, then they automatically keep multiple copies of your data for you and so on. Okay, so are there any questions about platforms? I just want you to know that it's basically something that makes it easier to write a cloud application. Okay, then on top of the platform, we have this notion of infrastructure. So the infrastructure is really the servers plus the network plus virtualization. And so this infrastructure thing, this is called infrastructure as a service. And examples are Amazon's web services. So if you're building an application at the infrastructure level using infrastructure as a service, this is this idea of renting this compute power, okay? This is, you're essentially renting a server. Okay, so can anyone, so basically, I don't know, you guys probably haven't used Amazon EC2 or anything, but what you get is when you start it up, you get a virtual machine, which is just essentially a server, a slice of a server, and you get this virtual machine. It has whatever operating system you want installed on it, and that's yours. You can do whatever you want to it. You can install whatever software on it. You can change settings, whatever you want, okay? So can someone tell me what a disadvantage of using this infrastructure as a service is versus building an application on top of a platform? Right, so if you're writing an application here and you're just renting a server and you want to scale it up, you want to get another server, you have to write that manually. It is possible, but in your code you have to say, oh, I noticed this is getting congested or whatever, and then I want to go to Amazon, ask them for another server, and then get that server and launch my application on there. Okay? So it makes it much more work for you as a programmer because you only have sort of the raw server. You don't have like nice things like this what platforms provide, okay? But could someone tell me, so that's a disadvantage, is that you don't get the benefits of a platform. But what's an advantage? Exactly, there's no constrictions in the platform, so it means it's more flexible, right? I mean, you have a server, you can do whatever you want with it. Go ahead, have fun. Okay, so in the remaining time, let's just briefly talk about, then finally, you know, what makes cloud computing new, right? So is it new? I'm not so sure. But one of the things that makes it newish is this idea of virtualization. And so virtualization allows you to use part of a server. Okay, it allows you to what's called slice a server. And so this slicing, you can think of it as like the analogy of if we have a pie and we take a slice of it, this is exactly what virtualization does. So we have our server, which is this pie here, and I come along and I say, oh, okay, I'd like to rent this quarter of your server. And so then I get this quarter, and because of virtualization, I'm isolated and I can only use this quarter of the server's resources, okay? So whatever that means I get, you know, say I get one CPU and I get like 2 gigabytes of RAM, and so on, okay? There's different resources on the server, you can slice these up. So with virtualization, it allows us to slice this server pie in any way we want and share this server with many different users, okay? And this was a key development in the building of cloud services, because with virtualization now we can all share the same resources. So you can go to Amazon and you can say, let me rent part of a server, and they'll give you, you know, you can rent a very small slice of a server for like 10 cents an hour. And so that's really what is new with cloud computing, okay? So just before we finish, I want to just briefly cover like what should you think about if you are doing a startup or something and you want to be in the cloud because this is the hot thing to do, right? But so do you guys have any idea of like why would you write an application for the cloud? Okay, yeah, so the advantage is your users can access it from anywhere, right? Now, if you write an application, say that's an iPhone app, your users can access that from anywhere. But what they can access here is they can access all the data, and they can access whatever sort of backend you have. Like if you have a complicated algorithm, it can run on the cloud, right, and not on somebody's iPhone. But so does anybody know another reason for using the cloud? Yeah, so it's sort of stable, I guess, because it's in a nice managed environment. You know, Amazon has nice data centers. It's stable, and so what you said is, you know, if you're running on your machine, you could run out of compute power. So there's practically unlimited compute power, right? I mean, it's not exactly unlimited, but for all intents and purposes, if you have 200,000 servers, that's unlimited for you, right? Anybody have any other ideas? Yeah, so you can run let's say flexibility, you can run any operating system. You can accept requests from any users running any web browser or any OS. Okay, any other? Yeah, so that's sort of what I was looking for, is the cost. So renting time on a cloud server is pretty inexpensive. It's probably less expensive than actually going out and buying that server yourself and paying for the electricity and paying for the cooling and paying for somebody to manage it, so on. And then also you can do, if your workload looks like something like this, where this is time, and this is the, let's say the demand or your load. So let's say you have an application that does something like this. Well, with cloud computing, as you need more, as you have more demand, you can rent more servers. So say there, and there, you rent a server, right? You need more resources, so you rent another server. But then as your users go away, you can release those servers, and so you only actually pay for the amount of computing power you need, right? Whereas if you didn't do cloud computing, you'd have to buy whatever your peak is here, you'd have to buy enough servers for that to meet that demand and always pay for those that always run them and so on. And that's it, thanks.